Doctor.
Okay. Question?
Yes, Doctor.
Yes.
Go ahead. The third quiz will be next week, right?
Yes, it will be on Wednesday, inshallah.
Inshallah. Thank you.
Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to E21. So today is our fourth lecture. And in this lecture, we're going to continue talking about Ohm's law. And we haven't started talking about Ohm's laws, but we introduced the notion of resistors. But going over what we've covered in the previous two lectures, we started with in the previous lecture, we defined current as the rate of change in the flow of charges. We defined voltage, or the potential difference, and we defined the power as a product of the voltage with the current, or the rate of change in the energy. And if you recall, in the previous lecture, we introduced the notion of electric sources, and we assumed that we have ID sources, and we classified them based on into two major classes: independent sources. Those sources have fixed voltage and current, no matter what the value of the other quantity. If they are voltage sources, they have a constant voltage no matter what the value of the current, and if they are current sources, they have a fixed current no matter what the value of the voltage. The other class is dependent sources or controlled sources. So for those sources are, again, and they have constant values, but this value, the value of the source, is actually determined by another quantity or another parameter in the circuit. We'll see them in actual circuits, inshallah, next lecture. Finally, we introduced the notion of the capacitors and the resistance, and we said that the resistance is the ability of the material, or the capacity of the material, to resist the flow of charges. And so far, we have three parameters. We have the voltage, the current, and the resistance, and we want to find a relation between them. It turns out there is a very fundamental law in electric circuits. It's called Ohm's law, and Ohm's law relates the voltage to the current and to the resistance. So Ohm's law states that V equals to I multiplied by R, and there is a positive or negative depending on the direction of the current flow. So if the current is flowing from the positive terminal to the negative terminal of the voltage, then we're going to use the positive sign. If the current is flowing in the opposite way, we're going to use the negative sign. Yes? Yes, Abdulaziz.
Yes, doctor. Are you sharing screen? Because I'm not seeing anything.
I'm sharing my screen. Can you see
We can see it.
Yeah, for me it works just fine.
Yeah, it's a bit.
Yeah.
Abdulaziz, you may need to actually rejoin the meeting again. This part will be
Okay, I'll try.
Good, very good. Okay, so we said that the V equals to I multiplied by R if the current is flowing from the higher potential to the lower potential side of the resistance, and the negative value is used when the current is flowing from the negative, from the low side, from the low potential to the high potential. And a very actually informative cartoon is this one. You can see here the high potential is creating a force. The high voltage potential is creating a force, and this force is pushing electrons into the material. Could be metal, for example. And the property of the resistance of the material is trying to stop or minimize this flow of electrons. So think about it this way: the force is kicking electrons into the material, and the resistance is trying to stop them from being stop charges from being transported inside the material. Yes, Ahmed.
دكتور يعني نقدر نقول ان الفولت وظيفته عكس وظيفة الريزيستنس voltage.
No, it's not that straightforward. It's kind of like, think about it this way: the voltage is kind of like creating a potential, creating a force, much like, for example, if you have a pump and the pumping start is pumping water into a pipe, okay, and you have somewhere in the pipe you have the ability to reduce the diameter or increase the diameter of that pipe. So the voltage will be a lot like the pump. The resistance is like the knob that you're using to reduce or increase the diameter of the pipe. Okay.
Okay, thanks.
ليلى.
ايه دكتور، طيب ليش احنا نحتاج انه نقلل الدايمتر حق البلب بالريزستنس، يعني نقلل الفلو اوف تشارجز؟
This one.
ايه ليش نحن نحتاج نقلل الفلو اوف تشارجز؟
This is just an example.
Okay.
Of course, the resistivity of the material depends on the cross section, but this is just like a cartoon. This is just to give you an. If you ever like want to understand the concept behind it, this could be something that should come into your mind.
Okay.
Yes, Munir.
I want to ask about the relation between the voltage and the resistance. This means that the more the voltage we have, the more resistance. Is that correct, Dr. Muhammad?
The more voltage, the more resistance. No, the resistance is a property of the material itself. Voltage is a force. It's something external, something you apply. For example, how to find a good example for that. For example, your name is Munir, right? Your name is. It's a bad example, so it's. Like I said, it's kind of like the resistance is a property of the material itself. Voltage is something external, something you apply. Yes, Ahmed.
It's clear. Thank you.
Okay. Good. Ahmed.
المعذرة كنت رافع من زمان.
Doctor, does this mean that the resistance is constant relative to the voltage and current?
Yes, the resistance is usually constant up to some level. So if you in most of the materials, the resistance is somehow constant. If you exceed certain limits, you're going to break. You're going to change this. The resistance will not be constant anymore. Take for example, if you have a light bulb and it's working with 110 volts. So what happens if you connect it to 22 volts? It will break, right? It has constant resistance, but if you apply as high voltage, this resistance will not be constant. It will change to a different value. In this case, it will become a short circuit. or an open circuit, depending on the material itself.
Thank you.
Okay, very good. Ahmed, I need to move on. Yes.
Okay, sorry, doctor, but just for clarify, can we say that the copper, for example, or the iron has the same resistance?
As what?
I mean,
Constant, you mean?
yeah.
Depending on the frequency, depending on the amount of voltage that you apply.
Okay, thanks.
But most of the time, for most of the applications that we have, we can say it's constant. Okay, one important quantity that's related to resistance is conductance, which is the exact opposite. So resistance is the ability or the material capacity to resist the flow of charges. Conductance is the material capacity to permit the flow of charges. So as you can guess here, they are the opposite. So the conductance, G, is 1 over R. You will see the conductance somehow is, the conductance is related to a parameter called the conductivity, which is it's related to the number of electrons that are available on the material to conduct charges, to conduct currents. Most of the time in this course we're going to use resistance, but if you're talking about, for example, if you're taking class in semiconductors, we usually prefer working with conductance. Okay. The unit of the conductance is Siemens or S or MHO, the opposite of ohm. So this is ohm, but spelled the other way. Okay, so now we define the conductance and the resistance. We defined the resistance in the previous lecture. We define now the conductance, which is exactly the opposite, the inverse of the resistance. Now let's see how we can use Ohm's law to how to utilize Ohm's law in power calculations. So we have P equals to V multiplied by I. We can use Ohm's law to find two different variants of this relation. It's either I squared multiplied by R or V squared divided by R. Let's derive it. So let's assume in this case we are, again, we can use one of the two conventions. The first one is we assign a positive voltage if the current is flowing from the higher potential to the lower potential. Let's just try to derive this equation using this convention here. Again, P equals to V multiplied by I. And if you recall from Ohm's law, V equals to I multiplied by R. And this is V multiplied by I. So I have I squared multiplied by R. So now we derived this one. So let's derive the other one. It's going to be exactly the same. But here I'm going to use Ohm's law to express the value of the current. So Ohm's law could be something like this, all right? It's exactly the same. So I divide both sides by R. So now I derive that one. So let's see what happens if I use the other convention. In particular, I'm interested in what happens here. Okay, let me just. Okay, according to the passive sign convention, what will be the expression for the power here? Rahim?
It will be negative IV.
It will be negative IV, or yes, it will be negative IV. So I have negative I. Then according to the convention we have here, what will be the voltage? I'm looking for new names. Okay. Ahmedani?
Negative IR.
Yes? Can you say it again, please?
Negative.
Yes, negative I multiplied by R. So if we expand it, we will get I squared multiplied by R. So as we can see here, we can do the same for V squared divided by R. So we'll end up with P always being positive. Resistance is always positive for this course. And we have I squared or V squared, so that means they are always positive, non-zero, greater than zero. So in this case, the power is always positive. What does it imply? Having a positive power. Abdullah al-Jariri. Abdullah. Okay, Amr Saleh.
It consumes energy.
Okay, exactly. It consumes energy or it dissipates energy. Very good. Okay, let's have an exercise here. Ahmed Nafi, question. Okay.
No, it was for participation.
Okay, good. So let's solve this exercise. What we have here, we have a bunch of circuits. We have 4 of them, and we are given either the voltage or the current, and we are asked to apply Ohm's law to find the other values. So if we're given the voltage, we need Ohm's law to find the current. If we're given the current, we need Ohm's law to find the voltage. So let's start with the first one. And for the first one, I need for the first one, Ali Talib.
Yes, doctor. The current is equal to positive +1 because it is in the direction of the resistance, and the resistance is 8.
Okay, very good.
So the voltage for A is equal 8.
Okay, exactly. So VA equals to 1 multiplied by 8, and this is going to be 8 volts. So what about the power? Who can give me the value of the power? Walid?
Yes, doctor. The value of the power is 8 watt.
It's 8 watts, which is I multiplied by V, which is 8 watts. Very good. So let's go to part B. And then okay, for part B, Ziad.
Okay, so the current is positive because it goes out of the positive.
Yes.
And the resistance is the reciprocal for the conductivity.
Yes.
Which means that the current is the V over R.
Okay, in this case, V divided by R, and in this case, we are not given R, we're given G. So G is 1 over R. So the current will be V multiplied by G. So IV is 10 ampere. Who gonna give me the value of the power? Dalal Yusuf.
It is 500.
It's, yes. It's V multiplied by I, which is 500 watts. Okay, very good. So let's go to the third part, part C. So for part C, let's see what we have here.
دكتور.
Yes.
بارت بي راح يكون باور 500 or minus 500.
Okay. Why minus 500?
Because the current is entering the voltage source by minus terminal side.
Okay, we're not interested in the power generated by the voltage source. So your point here makes sense. We're talking about the power generated by the voltage source, but here we're interested in the power dissipated in each resistor.
Okay.
So the 500 source is actually generating power, and the resistor is actually dissipating.
Okay, thanks.
Okay, part C. Let me find it. Yasser.
Yes. V is equal to minus on the negative side, so it is minus 20.
Minus 20 volts.
Yes.
I need Hassan al-Aboud.
Yes.
To calculate the power.
20.
Okay, the power will be, okay, minus I multiplied by V. So it's going to be minus 1, minus 20, and this is going to be 20 watts. Okay, very good. So part D. Let's see what we have here. Okay, let me find your name. Hassan Sayer.
Yes, doctor.
Yes. ID, what is it?
The I will be V over R, and it is negative.
Okay. So ID
50 over 25. Minus 50 over 25. So.
Minus 50 divided by 25, which is minus 2 amperes. The power, who's gonna give me the power? Okay, let me find Mohammed.
Yes, the power is going to be minus VI minus IV.
Exactly.
So it will be.
Let me just write your name. Okay. Minus VI. So it's going to be
minus 100 volt. Sorry, 100 volt. 100 volt.
50, and this is going to be
100 watts. Oh, sorry.
Exactly. So you notice here that the power is always positive, which makes sense because the resistor always dissipates energy. Okay. So let's move on to the questions. Ziad, Aziz. Okay, good. So let's move on to the second part, the second part in this lecture, which is about construction of a circuit model. Talal, yes. Yes, Talal.
Yes, sorry, Doctor. The fourth example. Why is the current negative?
Because
it's coming from the negative to the positive side.
The voltage source is in parallel with the resistance, so the current is flowing in the negative side here, to the positive side.
Oh, okay. Thank you.
Okay. So oftentimes you don't have a simple structure like this. You don't have, in reality, you don't have a circuit where, if you look into it, you will see a voltage source, a resistor, and cables that are connecting these two elements. What you have in general is something, an electrical system. So what you need to do is you need to actually take the actual components and try to model them, find something that approximates their behavior, either with resistor sources. Sometimes you need to actually go beyond this, finding like a nonlinear circuit elements. This is one occasion. So you have an electrical system and you want to model it. You want to find the circuit model for that. The other option is sometimes you have a black box. You cannot see what's going on inside of it. But what you can do is you can apply the voltage between its terminals and measure the current, or vice versa. So in this case, you may end up simplifying this black box by representing it with a resistor and some sources. And be aware here that this representation is valid over a short period or over a small set of voltages. So sometimes if you exceed that certain limit, you need to develop a new model for your system. Okay. So let's take an example here. Let's see. So we have a flashlight, and the flashlight consists of a battery and a lamp, and between them there are some components here. So there's a switch. The switch will turn on and off. If the switch is on, it means it acts like a short circuit. If the switch is off, it acts like an open circuit. So we have a bunch of resistors in series. So the first one is R1, which is the resistance of the connector. So the connector here, it has some resistance associated with it. So we need to model it. Then we have RC, the case. The case is made of metal, and that case is actually having some resistance associated with it. And finally, we have the resistance that we are interested in. which is RL, which is the resistance of the NAND. So the first two here, they are not desired. We don't want them, but they are there, so we need to model them because there are some voltage drop, there's some power dissipation is going to take place here. And there is the resistance that we are interested in, which is the resistance of the light bulb. And the battery here acts as a source. Yes, Salman.
Does the battery have resistance? Because in physics 102 they taught us that the battery have internal resistance.
Yes, very small resistance, yes. It does. If we want to get like a complete model, we can account for that. But remember, we're talking about ideal sources. So ideal sources don't have internal resistance, which means that they don't exist. Okay. So another way of, like I said, we can have a black box, a device that we are not familiar with what's going on inside of it. And we can apply voltage and measure the current. And that's what we did here. So we have a device here. We don't know what's going on inside of it. We apply a certain voltage. So we apply negative 40 volt. We measure the current absorbed or needed for this device, and we found that it's negative 10 ampere. Then we changed the voltage to negative 20, and we found out that the current is negative 5. We stopped if we didn't apply any current, if we didn't apply any voltage, then we didn't have any current. And we continue this. So we created a table of applied voltages and measured current. And what we want to do, we want to model this device as the following. Something with a resistance, maybe if we need to do, if we need to have a voltage source, but maybe a voltage source as well. But let's think about it this way. So we need to model it with a resistance here. So the very first step is you need to do is you need to plot it. So you plot the voltage versus the current. So the applied voltage will be something like this. So from the table, we saw that if the applied voltage is negative 40, if the applied voltage is negative 40, then the current is negative 10. Yes, Abdullah.
Why do we need to plot it? Can't we just use Ohm's law to figure the resistance?
Yes, we can do that. But I always prefer to plot it because if you plot it, it will reveal some useful information.
Okay.
It's okay to do that for this example, but sometimes you will see that, and I will explain in a minute, that you need to actually model it with something else. You need to model it with a voltage source here as well. So if you take one specific value and apply Ohm's law, there will be always like a shift, and you will not be able to catch it if you just take one row here, this row or that. So it's always good to plot it. So if we plot it, we say like when it's 40, it's -10. When it's -20, it's -5. And it will be something like this. So if we take the slope here, since this one passes through the origin, so the voltage source is going to be 0. If we take the slope here, we see that the slope is what? -20 minus 0, 5 minus 0 is equal to 4. So we can model this one as R multiplied by IT. And in this case, VT is 4 multiplied by R here is the slope. So 4 multiplied by IT. So if we model it, it will be something like this. Okay, any questions, Shabab? Okay, what we saw here is the following. We saw that sometimes we don't know what's going on inside a certain device, but we can apply a voltage and measure the current. And if we use this technique, we can come up with an equivalent. Remember, this one is equivalent. This is not exactly what's going on inside that. Not necessarily what's going on inside that. But this is an equivalent circuit model for the device that we have. As an example here, if you take, for example, if this one is, if the actual circuit is 8 ohm in parallel with 8 ohm, you should get exactly the same response. So there are infinite possibilities for there's infinite possibility for this circuit. But this one, this configuration is the equivalent. Is it clear?
Yes.
Okay, very good. Okay. So this lecture is actually one of the very fundamental lectures in this course because we covered Ohm's law, and in a few minutes we're going to cover Kirchhoffs law. And if you master Ohm's law, if you master Kirchhoffs law, you should get an A+ in this course. Yes, Ziad.
Can we get a non-straight line when we draw the plot, or does it have to be straight to obey Ohm's law?
You can get that, but in this case, you need to move to non-linear devices. So you're an electrical engineer. In this case, you will see this straight line, non-straight line. If we're talking about diodes, or if we're talking about limiting circuits, an E203. So we say that current is related to the voltage using Ohm's law. This is true for linear resistance. If you're talking about nonlinear devices, then they're not necessarily related by Ohm's law. As an example, you see that in E203, current, I don't want to write it, but current is related to the exponent of the voltage, the natural exponent of the voltage. Okay, very good question. Moving to Kirchhoffs law, if I ask you to solve a circuit, you need to find either the current or the voltage. So, or both. So you need, if you find the current and the voltage in every element, then you solve the circuits. Basically, you characterize, you have everything that you need out of the circuit. So you can characterize it, you can calculate the power, you can use it in any other system you have. So far, we studied Ohm's law. Ohm's law is very fundamental, but not enough. So we need some algebraic laws that are going to help us completely solve for circuits. And those laws are known as Kirchhoffs Law, after a German physicist. After a German physicist. So Kirchhoffs Law require defining the notion of nodes and loops. So what do we mean by node? So let's refer to this figure. So a node is a point where one or more circuit elements can meet. For example, here, this one, the entire point here, the entire the entire thing here is a node. Because this is the point where the 4 ohm resistance, the 20 ohm resistance, and the 80 ohm resistance are meeting. They are connected for this one. So this is the first node. What about this one? Is it a node? According to our definition. So our definition.
No.
Yes.
It's yes, because 2 or more circuit elements. So any 2 circuit elements should be connected by node. So this is the second node. Because this is the point where the 50-volt source and the 4 ohm resistance are connected. Finally, this is also a node. Because this is the point where the 50 volt, the 20 ohm, and the 80 ohm resistance are connected. Yes, Abdullah.
Doctor, is it okay for more than 2 elements to meet in one node?
Yes, and that's what we have here. So we have 3 elements. 50, 20, 80. And here we have 3 elements, 24 and 80. For node 1 and node 3.
Oh.
Okay, so remember the definition of that node is a point where 2 or more circuit elements meet. Yes, Ahmed.
يعني النود الحين لو امسك القلم واحركه من موضع الى اخر بدون لا اوقف، فكل هذا اللي امر عليه يعتبر نود كامل.
I did not quite get your point here. So
let's say, for example, if I put my pencil in the resistance, in the 80 resistance,
yes,
and I move it until reaching the 20, then return back, then going to the 50 volts. All of this is a node because I continue.
Yes, as long as you don't encounter any circuit element, this considered a node.
Thanks.
So another the notion of nodes, we're going to use it to define Kirchhoff's current law, and another important notion that we need to define is loops. So for loop is a path that's starting from an arbitrary node. So we choose a node here, and we start moving in a closed path until we get back to that node without passing through any intermediate node more than once. So let's see here. So let's assume that we start from this node. This is a node, right?
Yeah, same as 2, yes.
Yes. So we start here, then we go in a closed path until we reach this point. So this is considered as a loop. So this is the first loop. The second loop here is this one. So let me start from here. And then I will move in a closed path until I get to that point. So this is the second loop. The third loop is if I start from this point, for example, and I continue moving in the outer part of the circuit, and I get back here, and this is the third loop. Okay, remember, loop, I start from one node, go back in a closed path, and I don't return to the exact same node without passing through the any node more than once. Yes, an intermediate node. Yes, Ali.
Doctor, in the second loop, is it okay that it doesn't contain the voltmeter, or
Yes.
I mean the voltage?
Yes. Contains circuit element. So the voltage source is one circuit element, but it contains the 20 ohm resistance and 80 ohm resistance.
Okay, thank you.
You don't necessarily need to go through the voltage source. Yes, Abdul Karim.
Doctor, in the third node, if I start from where you start and goes by to the 80 ohm resistance, and instead of continuing, I go up with the 20 and pass again to the 4 ohm, is that still considered the loop?
No, because you're passing through this node, which is an intermediate node, more than once.
Okay, cool. Thank you.
Okay?
Yes, thank
So
you.
remember, you don't pass through an intermediate node more than once. Okay, very good. So now we know the definition of nodes, and let's actually study Kirchhoffs current law. Yes, Abdulaziz.
So, Doctor, can you restate the steps when solving a circuit?
Steps when solving circuit?
What's the best step to start with?
Okay, we'll come to it when we solve an exercise. So let's actually let's wait here. Let's pause for a while and define Kirchhoffs current law, Kirchhoffs voltage law, and then we'll move to an exercise. Okay. So Kirchhoffs current law states that the sum of all currents at any node in a circuit is equal to 0. So if you take any node and you sum all the currents going into that node, you should get 0. So this implies that you have as many currents entering the node as many currents leaving the node. So if you say like there's 20 ampere of current is entering the node, then we must have 20 ampere of current leaving that node. So think about it this way. If you have current is related to charges, right? Charges are conserved. If you have charges entering a node, then those charges must be leaving that node. Exactly the same amount of charges. So that's why Kirchhoffs law, Kirchhoffs current law, is derived from conservation charges. Okay, so this implies that we have to have positive, we can assign positive sign for current entering the node. And if we do that, the negative sign should be assigned for current leaving the node, and vice versa. Now, what happens if I have a node where only 2 elements? For example, this is the node that I'm talking about. So if I apply Kirchhoffs current law, KCL, I have this current I1, which is entering that node. I should have this current I2, which is leaving the node. So what can we say about the value of I1 and I2?
Equal?
They must be equal, yes. I1 must be equal. So in this case, if two elements are connected to a node, they must have the same current, and these two elements are called in series. So let's take an exercise here. Let's see. Let's take a specific node here. Let's take, for example, node A, and sum all the currents entering and leaving that node. So let us use positive for current leaving the node. So let's start with node A. Adnan?
4 plus 1.
Please. So I4 is what? Is leaving the node, صح?
Yes.
Okay. I4 is leaving the node, so it's positive here. What else?
I1 is leaving the node.
So plus I1.
Minus I2 and minus I5.
Minus I2, minus I5, what? Equals to what?
0.
Equals to 0, exactly. So let's see, Mahsen, for node B.
Yes, node B will be I minus I1
Node
plus
B.
I2.
This is node B, so it should be minus I1
plus I2.
plus I2.
The minus IA.
Minus IA, exactly.
Plus I3.
Plus I3.
Minus IB.
Minus IB equals to what?
0.
Equals to 0, yes. Remember guys, the sum of the current entering and leaving the node should be 0. The sum of the currents at any node should be 0. Excellent. So node C. So for node C, okay, let me find. Ahmed Al-Hamad.
Minus I3.
Minus I3, yes.
And minus IC.
Minus IC, yes.
And minus I4.
Minus I4, yes.
Just.
What about IB?
Yes, positive IB.
Positive IB equals to 0. Exactly. الجشي. Yes.
بس عندك بسألك عن سي.
Yes.
I4 is continuing into C.
Yes, because here there's no connection. Here it's like a jumping wall.
So it's not
connected.
Yeah, it's not separated.
It's not separated. Yes, there's no connection.
Thanks.
Jishi Ahmed?
I5 plus IC.
I5 plus IC.
Is IA connected to node D?
IA is connected, yes, to node D.
It is also positive. IA.
Okay, very good. Okay, excellent. Okay, we saw here how to apply KCL. So this is a direct application of KCL. Any questions, Shabab? So we need to sum all the currents, assign specific polarity for the current leaving, the opposite polarity for the current entering. Usually the convention is to assign positive for the current leaving, but you are free to do you are free to use any convention you want. And then you sum them and you should get 0. Yes. Any questions?
Yes, doctor.
Yes.
Sorry, but I didn't get how does the I4 continue to node C without...
There is no connection here. So I4 will continue here. And it will, this is not a connection. This is kind of like a jumper wire.
So it is not a node.
It's not a node. This is
okay.
not a node.
طيب دكتور, how can I know that? How can I?
Here is the connection is with bullet point in this circuit.
So if there is a black point, it means that the wires are connecting.
Yes.
Yeah. Thanks.
In this specific circuit. In this specific circuit. Okay. Any other questions, Shabab?
What about other circuits?
We'll see, inshallah, in other circuits. Right, Shabab, half of 8 of you are raising their hands. So if you don't have any question, we can move to the other parts. Ibrahim? Yes.
For node D, why the current A is not leaving out from it? Why it is positive?
IA is
yes.
This one. So you see that it's connected to you.
Oh, okay. Because there is other IA.
No, there's one IA.
Yes, I mean this.
Okay. There's one IA. Right, Shabab. Okay, I can answer that, but I need to move to KVL. I will get back after the class. Okay. Because we have 3 minutes. Okay. So I need to specify KVL. So for KVL, as Kirchhoffs voltage law is stating that the algebraic sum of all voltages around any closed path in the circuit is equal to 0. So if you sum all the voltage across all loops, you should get zeros. Across every loop, you sum all the voltage across every loop, you should get 0. So if you assign positive sign for the voltage rise, you should get, for the rising voltage, you should get a negative sign for the dropping voltage. Here, think about it this way. Remember, voltage is a potential difference. So think about it in terms of height. So if I ask you to find, if this is a building, and I'm asking you to find the potential energy between point A and you move to another building here, B, and then you get back to A. If I ask you to find the potential difference between the starting point and the end point, it's exactly the same. So this one has specific potential energy. And since you are moving in a closed loop, you should get exactly the same potential energy. So that's why the difference between them, they have the same difference. So the difference between them is 0. And that's where KBL is. And that's how to draw an analogy with potential energy. Any question? Okay. I really want to solve this one, but now it's 11:30. Hold on a second. So I will stop here. So far, let me double check the. I got 39 responses, which is good. Only one is missing, and 38 are okay with changing the time, and one is not okay. So I will contact that person, see if he's okay with changing the time. Okay. Next class, inshallah, I will solve this one, or maybe I will solve it and post it. Let me solve it with you, and we'll solve some exercises associated with KBL. Yes, Shabab. If you have any question, please.
دكتور يعني ننتظر منك ايميل على دوام بكره ولا يبدا من الاسبوع الجاي؟
Well, we cannot do anything for tomorrow because we need to plan it on a weekly basis. So we're taking 15 minutes. This means that over the course of a week, we are getting the same contact hours. الحين عندنا كل كلاس ساعة صح؟
صحيح.
إذا أخذنا 15 دقيقة أضفناها على كل باقي الكلاسات كم يكون مجموع؟
ساعة.
So we cannot change it on a single day. So it has to be done on a weekly basis. So I will see who hasn't responded yet, and I will check with that person who said he cannot to see if he's okay with that. Any other questions, شباب؟
إيه دكتور متى بتنزل الواجب ذا الأسبوع؟ متى بتسليم؟
Okay. For the homework, it will be assigned, inshallah, in the common. You guys have access to the common E201 section on Blackboard, صح?
صح.
Here practice exercises. For the homework, it will be, inshallah, assigned over there. It will be, inshallah, tomorrow, I think 12 or midnight, something around this.
دكتور بيكون الفترة أسبوع عشان سبمت.
Almost, yes. Almost.
دكتور.
طيب. تفضل.
دكتور ممكن توضح نقطة التقاط الوايرات اللاينات، كيف أفرق بين
This one?
Yes.
This is
in general, I mean, not especially for this.
No, usually this is kind of like a special case where we have, if we want to draw this circuit usually, we draw it this way. In a much better way, we draw it, for example, let's take this portion here. So we draw it something like this. There is a kind of like a jumper here. But this is taken from your book, and your book draw it this way. So it's your book's fault. But usually we will not encounter such, if we encounter such a situation, so in general, 99% of the time, if you have this kind of connection, then there should be some sort of connection. If you have this kind of communication, there should be a connection here. It should be a node. But for this particular example, it's not a node. Because here the junction is specified with the port points. Is it clear?
Yeah, it's clear.
So if you take, okay, this is one of the exercises that I was planning to solve. So usually your book is doing it this way. If there is a connection, it's the book writes it like this. I don't usually do it this way. I usually avoid having bullet points.
So in general, it doesn't matter if there is a blank point or not.
Doesn't. Yeah, in general, it doesn't matter. In general, it's connected. But for this particular part of the course, because we're talking about nodes and definitions, so we kind of like emphasize where the point is connected. But if you go, for example, to something more advanced, you will see that this kind of bullet point is not there anymore.
Okay, thanks.
Salman? Salman?
Yes. Can you go back to the current Kirchhoff law? Yes, this page.
Yes, go ahead.
I mean الرسمة الصفحة اللي بعد في نود دي كيف كل الكرنت طالع من النود ما في كرنت داخل. We have three currents, all of them positive and equal to 0.
Okay. Here's the thing. I5 is an assumption, صح?
Yes.
We assume that the direction of the current is leaving that node.
Yes.
So if we solve for it, we'll see that if we have all the needed values, we'll see that the I5 is actually negative, which means I5 is entering the node. It's not leaving the node. So those kind of like assumption, that's what we need when we solve circuit analysis. We always assume a direction. If we got positive, it means that our assumption is correct with regards to direction. If we got negative, it means that our assumption is incorrect with regards to the direction. Okay, good.
Doctor?
Ali?
Doctor, I didn't get how to why you plot IA, the current A.
Why?
In the node D, I mean.
Yeah, IA is connected here. You see that IA is this one. This is IA. IA is the current of the current source.
Oh, okay. So what about I4?
I4 is connected here. It's going this way.
But it didn't enter the node D, or?
No, it doesn't. There's no connection here.
Okay. Thank you. It's clear now.
Ziad?
Can you both go to the exercise with the 4 figures? I think it was in the beginning of the lecture. Yes, to the solution. Someone said in exercise in figure C that the power for the source should be negative and you said it makes sense, but it didn't make sense for me.
So if I ask you to calculate the power, actually the question was on this one, not on that one, but it should be the same. If I ask you to calculate the power generated by the source, what should you do here? So V multiplied by I.
Yes.
Okay, so V multiplied by I. According to the passive sign convention, this is positive, صح?
Yes.
So V, what will be the value of V? Negative 20, صح? We calculated V.
Okay. So
multiplied by 1, which is negative 20. You can see here that the source is negative, the power is negative, which means that the source is generating power, and the value and the resistor is dissipating the power. So if you sum all the power here, power generated will be equal to power dissipated.
okay. Thank you.
Yeah, so far any confusion. Good. Amar?
Yes, doctor. The quiz is going to be in class time, right? On Wednesday.
Yes.
And the material is the same as posted in the syllabus, right?
Yes, which is this week's material.
And it's going to be written or multiple choice?
Most likely it's going to be written.
And how about the homework? Written or multiple choice?
Homework, I think it's written. I'm not the one who's going to write it this time, but I believe it's written.
Okay, thank you very much, doctor.
Okay, no other question? Okay, we'll see you inshallah next class.